Start recording. So it's a pleasure to have Anson Hook from Maryland University here with us. He'll be talking about fun with cosmic strings, a CMB Millikan experiment, and colliders in the sky. So take it away, Anson.
Yeah, thanks for having me virtually, at least. Yeah, so today I was just going to tell you guys about cosmic strings and some sort of progress and sort of thoughts along these directions. So I suspect you guys are very similar to me in that sort of, at least my personal ultimate goal is to sort of try to find out what's the sort of microscopic theory of the universe. So I want to sort of find all the particles and their interactions. And so the way people normally do this, right, you're all familiar, is we basically abuse quantum mechanics and Einstein, which basically says, quantum mechanics says if anything is not forbidden, it's possible. And Einstein just says all you need is energy. So if you just smash stuff together with as much energy as possible, magic can happen, and then we can just look for whatever flies out. However, this approach doesn't work if you don't have enough energy to produce everything. And so if you want to learn about the ultraviolet theory, what happens is you need to sort of make assumptions about intervening physics. And you can learn something about the ultraviolet physics modulo these assumptions. So, of course, my goal is to actually learn as much about the UV as possible. And it turns out there's a nice way of doing this via topology, right? So if we talk to any of our condensed matter friends, you know, they really like topology these days. And the reason is that anything that's topological is really, really robust. In particular, topological objects in field theory are RG invariant. And so they don't change as you go from the UV to the IR or vice versa. And so if you can actually measure these topological objects, then you really learn something about the ultraviolet of your theory. So your first thing is say, well, how do we measure topological effects? What's something topological? Sort of one of the first things you sort of learn that sort of has the feel of something topological is sort of things like, say, like the Aharonov-Bohm effect, where if you take an electron around a magnetic flux, then it acquires a phase. Now, you can then ask, okay, we've discovered the theory, the standard model. What are its topological objects, or sort of the closest things it has to something topological? And sort of the closest things it has are these sort of theta terms, which have been very well studied, right? The theta of E and M controls the electric charge of monopoles. There's the theta of SU2, which you can do a B plus L rotation to get rid of it. Or more accurately, is some linear combination of SU2 and U1. And the last one is sort of the GG tilde coupling, and is sort of tied to the strong CP problem. So two of these we cannot experimentally probe, either because it's unphysical or because we don't have monopoles. And the last one is a well-studied topic. So in the standard model, this sort of option is well explored. However, what you can do is go to the BSM, and by far the most famous BSM topological object is sort of called the 't Hooft anomaly. It's something, anomaly matching is very famous, and the fact that it's RG invariant is really used very heavily. And so you can ask then, how can you measure the 't Hooft anomaly?
Wait, I have a question. Why are you calling the 't Hooft anomalies BSM objects? What do you mean?
Because in the standard
of QFT, not BSM.
Well, yes, I would say the standard model itself. Well, I guess you can use 't Hooft anomalies even for, let's say, pion decays.
There are huge numbers of 't Hooft anomalies in the standard model that are matched by the standard model.
Yeah, and so I think the statement is I'm going to just. It's easy. The standard model has been explored to death. So I want to just to do something new, I have to go beyond the standard model. And so I'm just going to say, explore the 't Hooft anomaly in some BSM physics.
Okay, thanks.
Yep. And
but you mean that it is still associated with QCD, or in this sense, or because this theta angle, it is rather associated with axial anomaly, not with 't Hooft anomaly, right?
Yeah, so the one I'm actually going to be talking about is literally this coupling, which is the coupling to the photon, and not QCD. So I'll probably say axions in this talk, and what I really mean is axion-like particles. I'm just too lazy to say axion-like particle.
I see. So in this way, you can forget about QCD, right?
Yeah, that's right. And I'm actually going to entirely talk about photons, or its interaction with photons in light. Yeah. And so this is the sort of axion-photon coupling I'm going to be looking at. And this script A here is the object that's called the 't Hooft anomaly. However, you'll notice whenever anyone talks about these sort of axion-photon couplings, they basically never write it like this and never talk about the 't Hooft anomaly. They talk about this GA gamma gamma object. And the reason why is most ways of detecting axions is sensitive to the decay constant of the axion F. And this decay constant is annoying because it does RG evolve. And if you're not measuring the 't Hooft anomaly, you're not really measuring something sort of about the ultraviolet of your theory at all. You're really only measuring the sort of decay constant up to some constants. And so if you want to really measure the 't Hooft anomaly, then you have to have something that's independent of the decay constant, independent of F. And so it turns out that a really natural way of looking for these 't Hooft anomalies is by looking at strings. So strings are really nice objects because if you go around them, this angular field, the axion, goes from 0 to 2 pi. And you'll notice there's no F here. And so you can sort of hope that some measurements of strings can be independent of your decay constant. And it turns out that's correct. There's something like an
I'm sorry, Anson.
Yeah.
What do you call strings? Strings made of what? Is magnetic flux or what?
So here's the string, axion string is where at the very center, the U1 symmetry is restored. And as you go around it, there's a winding number, non-zero winding of the axion field.
Right. So you mean the things made out of axions or axion field, or what
Yes.
kind of field is inside?
Inside, it's going to be the axion and the radial mode, both of them. And the radial mode.
Pechi-Quinn-Higgs. Okay.
Yeah.
I missed it. Axion and which other field?
The radial mode, or the sort of the Pechi-Quinn-Higgs field.
So not electromagnetic field. So it's not like you know.
That's right. So this is a pure sort of a string object because the axion is associated with a U1, which can have non-trivial winding when you go around a 1+1 dimensional object like this.
Yeah, but you know, for this effect to be there, you need some kind of long range, right? So which field goes?
The long range interaction is the axion. For example, if you calculate the energy of this thing, it's logarithmically divergent.
Okay, right. But if axion has a mass, then it's not long range, right?
Yes. Well, it turns into domain walls, essentially.
Yeah.
And so, at least for simplicity, I'm just going to be discussing massless axions, or in particular, much lighter than Hubble today. So you can effectively ignore their mass. Well, whether or not how often this happens is a separate question, but at least for now, I'm just going to take it as an assumption.
And you're also going to assume that these particles, you're just going to introduce the parameters for these particles just to see this effect, and you're not going to try and solve some other problem like dark matter or anything else, right?
Yep.
I see.
So I'm not solving any problems with these new particles. It's more of just, if these guys were around, we could actually learn something about the UV.
But
okay. Yeah.
But then I'm not sure. For example, if it would be analog of Bohm-Aharonov effect, then let's say that you consider scattering of the string, right? Would it be a shift of different, interference picture, or or it would be no shift? Because I'm not sure, because this Hopf anomaly, it is like discrete one, right? It's not the same. So it would be no analog of Bohm-Aharonov shift of the interference picture, or it would be.
Yeah, so in this case, the sort of Aharonov-Bohm comes from as you take photons around this guy. And so you would get like an interference effect if you took this guy going to the left and interfered it with the guy going to the right.
I see. So it would be a shift of interference here.
Yeah. So it depends on what experiment you do exactly. For example, a phase shift for circularly polarized light is sort of rotations of linearly polarized light. And so rather than interference, you could just look for the plane of polarization sort of slowly rotating and things like that.
What if I take an electron and I drag it around the Axion string? Does it pick up an Aharonov-Bohm phase?
The Axion does not, or sorry, the electron does not, because if you look at the electron coupling to the Axion, it's not actually quantized or anything like that. And to get something Aharonov-Bohm like, you need sort of something very like quantized.
Yeah, no, but you see, the interaction of axion with the electromagnetic field is the one which doesn't contain contains field strength. It doesn't contain potential, right? So if you look at interaction of the form A F mu, right? Then but what you have in mind, I think that it corresponds to some kind of mixed picture when you are writing this in a form where derivative is axion on axion field, right? And then you have kind of, this mixed type of interaction where you have potential, electromagnetic potential, as well as derivative of A.
Yes, that's right.
I just wonder, it's probably should be important for you. That's why I'm asking about this.
Yes, that's right. Yeah. So when deriving all these things, you do actually integrate by parts. So you have the derivative on the axion times whatever the k mu current, like A dA.
Yeah, is what, right? I see. So in this way, it is then becomes more closer to this topological currents or whatever, right?
Yes,
I mean,
that's right.
Can I follow up on my question?
Yeah.
If I compute a Wilson loop for the electromagnetic field for A mu, the standard A mu, around an axion string, is it non-trivial or is it trivial?
It is non-trivial.
Then an electron will pick up a phase. The electron couples to ENM. It doesn't have to couple to your axion-like particle, strictly speaking. What if it doesn't?
Yeah. Okay. Yeah.
But it couples to ENM, and if a Wilson loop is non-trivial, then an electron.
Yeah, and an electron.
Phase. So
sorry. Let me. No, I might have to. I might have that statement wrong.
But he means in this way.
Okay.
But you can consider, Alexei, you can consider photonic Wilson loop.
Yeah, a photonic Wilson loop will carry one, but
yeah, you see, when you have something in the loop which is a probe, which but it's very different, because in this way, photon is massless object, and normally Wilson loop is associated with something which normally you would see like a heavy probe, right? I mean, massive probe. So in this way, it's not Wilson loop in the usual sense.
Okay, maybe once Anson goes on, it will become clearer precisely which Wilson loop he has in mind.
No,
so
but just
okay.
Since everyone is jumping, I feel that I need to jump as well. So d mu A, small a, times capital A F dual, right? It's basically a coupling, as you said, of a spin of a photon to a gradient of the axion, right? Because A F dual, so it's there is an epsilon ijk, right? So if you think of a real photon, it would be an operator that corresponds to a spin of a photon. Okay, that's what it is, and that's why it gives a different phase for left and right polarized particles, because spin points to along or opposite to propagation.
Yeah,
right?
no, but
and if I take a coupling to an electron, it's the same coupling, right? I take d mu A times the axial vector current of electron, which is exactly the spin of electron times the gradient of the Axion field. So just looking at these things, why wouldn't be there an effect for an electron, for example?
Oh, I think the statement is that it's not quantized. So it depends on your radius, for example, that you go around and things like other things, because it's the end effect is sort of RG, like the coupling is RG non-invariant, right?
Yeah, but also, Maxim, what you are suggesting, FF dual, it is a helicity of the photon, right?
Right.
Yeah, so in this way, yeah, even just in this form, you can say that it's different for it react to helicity of the photon, right? It gives the different contribution for different helicities.
Yeah, but so there will be you know, for an electron, it's very similar, right? It's a coupling of d mu a to the spin, right?
No, I'm trying to say that even in the form where it's not d mu a, it is still differentiate between helicity of the photons, right?
Well, a times psi bar gamma mu psi also proportional to there is a dependence on helicity, right?
No, I understand. No, the difference is still is that in one case, when I'm talking about helicity of the photon, I'm not putting d mu a, and what you are saying, it is d mu a, right? Yeah. So, for example, for static a, it would be difference in helicities, right?
Oh, for static A, you have nothing really.
What?
I mean, like unless you have a string, right? But for static A is just a boundary condition, right?
No. Static A is equivalent of theta. So you do have an effect. Why not?
Because it's an electromagnetic field. You don't, right? I mean, you have to have non-trivial boundary condition.
No, right. No. So in principle, there is could be theta dependence. Yeah, I mean, in electromagnetic, right? Depending on how we arrange the theory, right?
But
No,
it's the same thing for electrons, right? If you have non-trivial boundary conditions for electrons, you will have it as well. Maybe it's not quantized. That's different, right? But there will be an effect on electrons because the nature of the coupling is a spin times the gradient of A. That's all.
No. For electron, I would say that it would reflect it in the mass storm rather, right? Because mass storm is the one which provides you the theta dependence.
No, it gives a precession of the spin. If there is a spatial gradient of A, there is a precession of...
Yeah, no, I'm not talking about constant time.
Yeah, okay. So I have to. So you're saying that for electron there will be no. So if I go to the region where A is nil, there will be no effect, right?
Yeah.
So the question is, if I take an electron around the loop, do I get any effect? Right? Sorry, I didn't mean.
This is easily answerable, right? If you solve the equations for an Axion vortex, you can compute a Wilson loop at long distance around the vortex, and either it's non-trivial or it's trivial. You just find out.
Okay, so sort of the main point I was trying to make here is at least that the effects are independent of F. So you can at least in principle be sensitive to sort of these more topological quantities. Sort of another experiment which you can do, which is very similar in that it's also independent of F, is basically that these strings, I'll prove later, happen to be superconductors. They have zero resistance. And so basically anything associated with Faraday's law and these guys actually turns out to be also independent of F. and depends on, for example, B field, geometry, and things like that, but is independent of your decay constant. So in principle, if you had a laboratory experiment, you could actually measure these anomalies. We won't have strings in the lab, so it'll be very difficult to measure these anomalies from this project. But in the end, they're also sort of sensitive to sort of the anomaly and the anomaly alone.
What do you mean by saying strings are superconductors? Does it mean that the photon has a mass in the core of the string?
Yeah, so that statement depends. So the statement that I can prove is that there are massless particles, massless charged particles on the string, and that di dt equals 0. I'll probably actually get to that in like 10 minutes and actually proving that statement. But they're well, whether you call them superconductors or not, they have zero resistance. They also happen to be really, really, really thin, so you don't get the Meissner effect. But yeah, they happen to be, you can show that they have R equals 0 at least. Okay, so this is basically going to be what I'm talking about today, is just how to strings plus this coupling and seeing how can you use this combination to measure these anomalies. So my somewhat ambitious outline, we'll see how much I get to, is first I wanted to actually tell you what's the sort of, what you get out of all this. I'm going to sort of prove that this anomaly coefficient A is a measurement of charge quantization up to some integer that you can't prove. Then I'll sort of talk about how photons affect strings. So this is these Faraday law type experiments that may or may not be going on in the universe, sort of prove that they're superconducting, and then sort of talk about how to look for them. And at the end, if I have time, I'll sort of go over sort of progress on a subject that you guys might have heard about a year or so ago, about how to, these Aharonov-Bohm effects and how to look for them in the CMB.
Excuse me. So, but on the other hand, you may say that when cosmic strings move and intertangle, they are antennas for such axions, right?
Yes, that's right.
They emit a lot of them.
They emit a lot of axions, that's right.
Because you just add this interaction, you see, and it's okay.
Yeah, and so in some sense, the advantage of looking at these sort of photons types is because photons are easier to see than axions. If they were equally easy to see, you would just look for the axions because the axions are just produced a lot more than any photons.
Yeah, I'm reacting that you discovered a new person in the field, because Aharonov, it is something new, right?
Oh, did I misspell it? Oh, oh, whoops. Yes. I found some new person in the field.
Not so easy to detect such things, because our eye recognizes the whole world. You know, you can write more or less interchanging letters as you want, and up to a certain level, people will still read the text correctly.
Yeah. All right. Okay, so let me try to argue that basically this is sort of a well-known thing, but in case people haven't seen it before, sort of argue that 't Hooft anomalies tell you about quantization of electric charge up to some integer. And to see this, you sort of look at this coupling to the photons, and you say the axion is a periodic field. It can change by 2 pi. And you'll notice, though, that this coupling is not 2 pi invariant. So as you change A over F by 2 pi, the theta angle is effectively changing by 2 pi times your anomaly. So the question is just then, what this teaches us is that it teaches us about the periodicity of the theta angle, and of theta angle of E and M in particular. If this was a non-abelian field, we know non-abelian theta angles are always 2 pi periodic. And so then you can just show straight off the bat for any non-abelian coupling that this anomaly is an integer. However, for photons, it is not quite the case. This is sort of the famous thing of whether or not the standard model of the gauge group is modded out by Z3 or Z6 and whatnot. And that's actually all reflected in what is the periodicity of the theta angle. And so this theta angle, the periodicity of the theta angle is what teaches us about charge quantization. And the way to see this is to use the Witten effect. Right, so the Witten effect says that the electric charge of any monopole is proportional to the theta angle. And of course, you look at the formula, and it is also not 2 pi periodic or periodic in anything. And so what happens is that under theta goes to theta plus its period, the monopoles are exchanged with each other, right? A charge -2 monopole turns into charge 1, turns into charge 0, turns into charge 1, turns into charge 2. And so really what the periodicity of the theta angle is telling us is about the difference in electric charge of monopoles. Right.
But when you're saying, okay, if it would be pure abelian theory, you can wonder if there are some, but because monopoles in certain sense are reflection of non-abelian nature of the theory. So in this way, if it's a pure abelian theory, then monopoles are not there, and then it's not kind of observable theta, right?
Yeah, that's right. So I'm making some implicit assumptions, for example, of U1 versus R versus what 't Hooft loops or Wilson loops are allowed in your theory and all that.
Right. So, but in this way, it implies that it is a part of in certain sense, non-abelian construction, right? Because otherwise, I do not see how you can, see any theta dependence. No, I mean.
Yeah, that's right.
Okay, okay.
So there is an implicit assumption like that in there,
yeah.
yes. Yeah. And so what you can then ask, though, is that the difference in these electric charges of a monopole should be some integer times the fundamental value of electric charge, right? Because I, in some sense, assumed U1, and I've assumed sort of charge quantization and whatnot. And so you can just ask that this be true. And what you find, basically, well, with mild assumptions about U1 and whatnot, that this 't Hooft anomaly has to be some integer times the sort of fundamental unit of electric charge squared. I'd normalized everything in the standard normalization that electron has charge 1. So if you measure a fractional value of this guy, then you've discovered that charge is not quantized in units of the electron. For example, you might imagine that this is 1/9 because of down quarks and things like that. So the payoff, if you can actually measure this object, is it really is something like a Millikan experiment. It's annoying because there's this integer here that we don't know what it is, but it is Millikan-like. Okay.
I'm sorry, can I ask another quick question?
Sure.
Normally when we say there's an 't Hooft anomaly, we say which symmetry has the 't Hooft anomaly.
Yes, that's right. And in this case, it's the Axion shift symmetry. Axion goes to Axion plus 2 pi. So Axion is non-linearly realized as a U1 symmetry. And here it's that U1 times U1 E and M squared.
I see. Thank you.
Yeah. Okay, so the first thing I'm going to talk about, because at least some subset of the people, first thing I'm going to talk about is basically Faraday's law acting on strings. And so people at Minnesota have written many papers on anomaly inflow and sort of how this works for strings. I am significantly less mathematically inclined than a lot of people, so I'm going to actually just give a physics argument for why strings are superconducting. There's a mathematical one, which is basically just saying this coupling is not gauge invariant in the presence of strings, and so that the anomaly, the fact that this non-gauge invariance has to be canceled by a non-gauge invariance on the string itself. But let's do this with a physical argument. And so what I'm going to use is the fact that because I've introduced a coupling to E and M, when you calculate the electromagnetic current, there's this sort of, this has a name, Goldstone-Wilczek, I think. Well, either way, you can just apply Noether's theorem in the presence of an axion, and you get that axions carry current. In particular, gradients or time derivatives of the axion times F have electromagnetic effects. This is basically how we detect axions, right? You put a B field here, a time derivative here, and then we look for the current. That's the 0th order how every axion experiment looks for axions. And so we can take this current and just say we have a string and an electric field that's parallel to the string. What you can do is then just calculate the current, and you discover that there's a current that's non-zero that's pointing inwards towards the string. So if charge is conserved, charge must be flowing onto the string when electric fields are parallel to these strings. Now, that means the theory of a string plus an electric field must have particles and charge appearing out of nowhere on top of it. So if you say first, our particles are appearing on the string, at least my first thought is something like Schwinger pair production, right? That's a way to produce particles out of nowhere with electric fields. And the standard Schwinger pair production has an exponential suppression, right? It's hard to produce massive particles. And if you look at the current we're trying to match, there are no exponentials here. So in other words, the particles that we're producing must be massless so that you can produce them without an exponential suppression. The next thing you have to do is that you say, well, Schwinger pair production produces pairs, right? It doesn't violate electric charge. It creates a positron going to the right or an electron going to the left or something like that. And so if you want to create charge out of nowhere, because charge is flowing onto the string, you have to forbid left-handed particles moving in the left direction. You say there are only particles moving to the right. This is another way in 2 dimensions of saying that there's an anomaly, but this is sort of physically what you do. You just take the pair out of Schwinger pair production. You remove 1/2 left moving particles. And if you just plug in the math, you actually even get the order 1 numbers right in this sort of toy explanation I gave. And you find that the charge flowing in from this sort of axion current is matched by particles being produced out of nowhere on the string. And so you see that even though strings particle charges are appearing out of nowhere, total charge is conserved. And the statement of the anomaly is that we have massless charged particles moving in only one of the 2 directions, only right-handed moving right down the string, or rather than moving left down the string.
No, but what you say, does it imply that your string had the charge, for example, and this charge is diminishing in time, or what's going on with the string charge?
The string charge is increasing as a function of time because it has an electric field on there. And so you can either say that it's pair producing particle, or not pair, but just producing particles out of nowhere, or you can say that they're accelerating them out of the Fermi sea, or whichever your favorite.
It could be, but it could be also decreasing in time. Imagine that you have a string already with a charge.
Yeah, so depending on the sign here, it's this anomaly positive.
Yeah, is what I'm asking, right?
Yeah.
Right.
That's right. So what you can't actually prove what particles exist on the string, but you can prove that they are there's some sort of anomaly here, and they're more right movers than left movers, and maybe their charges are different. So now let's try to use this anomaly to prove that these strings are superconducting. So what you can do is you take a uniform charged string in the absence of an electric field. And so the divergence is the time derivative of the current, or time derivative of the charge density plus the gradients of the current. And because I said it was a uniform string, the I is not changing with space, right? The current is not spatially dependent. And so the divergence of charge here is just d lambda dt. And there's no electric field, so this right-hand side is 0. So what you see is that d charge density, d time equals 0. However, these are massless particles. So their charge equals their current. Now there's a little bit of a subtlety involving, you might have plus charged guys going to the right with charge 1/3, and minus charged guys going to the left with charge minus 1/5 or something. And so you don't know exactly what this proportionality constant is, but you can show that there's going to be some proportionality constant. It could be 1 in the case of a single particle, right? Because it's massless, it's moving at the speed of light, so its charge density equals its current. And by the anomaly, then that's 0. So these objects are superconducting, or at least they have no resistance. If you have a current on them, it doesn't change in time. Okay. So let's start talking about currents in the real world, like what sort of things you can actually get. And so I'm going to be going through a bit of undergraduate E&M of just Lenz's law or Faraday's law for a string that's moving through the B field of a galaxy. You get some Lenz law current because the flux is changing as a function of time. And in fact, if it was a superconductor, you know exactly the answer, like, the Meissner effect. Namely, you know that the total flux inside is 0 forever. So a superconductor would screen all flux. So there's a tiny little bit of math you can go through, which you can basically say, you can calculate what is the current on the string in terms of the flux that enters. In particular, you sort of re-express the change in charge in terms of the divergence of the current. You can use the anomaly to turn this into an electric field. You apply sort of line integral of electric fields being sort of d fluxes d times. And you see that basically the charge that enters onto the string is equal to the amount of flux that passed over it. And if you take sort of derivatives of the above, then time or space multiplying by some speed of velocities, you can see that the current is proportional to the change in flux. And it's a little bit of math, not a little bit more math, where you can say the current on the string is proportional to how much flux enters. The amount of flux entering has a contribution from your self-inductance. And doing a little bit of math, you find that the total flux entering is equal to the applied flux divided by a log. In particular, the fact that this is not 0 means that these strings are not, they don't have the Meissner effect. They don't 100% screen the magnetic field, but if you put in order 1 numbers and everything here, for example, Hubble-sized string loops and things like that, then you'll get this thing is suppressed by an order 1 number here. Okay. Actually, let's skip this. So
I think I missed some argument earlier.
Sure.
What's the argument that you only take the left movers here in this screening discussion? And also in the earlier part for the superconducting argument, what takes you, to only take the electron and remove the other half?
Yeah, so you'll notice here that there's a current, an Axion current flowing onto the string. And right, so this is, so if current is flowing onto an object, its charge is increasing. Now, if you look at typical Schwinger pair production, it produces both minus and plus charged objects. And so it creates particles, but it doesn't create charge. You need to create charge out of nowhere. And so to make it violate charge, you just remove left movers and keep only the right movers. And so this is how you can actually create charge out of nothing on top of a string. which is another way of just saying an anomaly is the statement that charge is not being conserved. And so this is how you sort of create charge out of nowhere.
Okay. So it's still basically the picture. I have a current flowing into the string. The current itself implies the increase in charge. Let's call that.
Yeah.
Yeah.
Yep. Yeah.
Is this strict document in the sense? I think in our current in our normal ENM experience, like for point-like particles, this is true. Is it also true for some like a dipole pairs or something like that?
I mean, I think maybe the analogy to think about is a capacitor where you have sort of current flowing in, and then the current ends on some object and so that charge of that capacitor is increasing if there's current flowing on. So you can sort of, if you want to, you could imagine.
Yeah, I certainly understand the analogy here in a simple picture. Okay, but later on you only take the left movers. Is it of the same reason for the screening or some different?
Yeah, it's this argument here. You say only one of the two directions are particles allowed to move. And so you take an Axion strings, particles are only moving in one direction along the string.
Okay. Thanks.
Yeah. Let's see, where was it? All right, so the sort of surprising thing you can do then is actually just calculate what is the current on the string, all right? And if you put in a galaxy-sized object, so 10 kiloparsecs in size, micro Gauss B fields, usually numerical simulations indicate strings are moving at sort of 0.1 velocities. And just plug in these numbers and you get a current that's about 10 to the 8 to 10 to the 9 GeV. So these things are huge, like a huge amount of charge. And remember, this is not just charge, it's charge and current. And so you can see why this is sort of could be very visible, because if you have charges of 10 to the 8, 10 to the 9 GeV, let's see, I'm a little short on time, so I might not get into bound states. But so to describe these guys, I'm just gonna sort of talk briefly. You remember that this has current and charge densities of order 10 to the 8 to 10 to the 9 GeV. So these are huge electric charges. So this means the electric and magnetic fields around these currents are huge, right? And so you can ask then, well, you have a huge electric charge. It's going to neutralize by pulling stuff from the plasma. What do these bound states look like? And the answer is it looks very much like an atom, in that you're going to get shells of bound states that sort of neutralize its charge, right? Just like a highly charged nucleus gets surrounded by a lot of electrons. You can go through, do a WKB approximation. It's not important. But doing a WKB analysis of just a charged string, what you get is that the radius of the bound states are roughly an integer over the charge density, which you probably could have guessed by dimensional analysis, and that the bound state energies are of order charge densities and only logarithmically depending on the sort of quantized n. So again, radius, yeah.
When in your picture it looks like rather the main walls than the string, right? But you still have in mind that it is not in two spatial dimension. You mean it is in 3D, right? In 3D,
yes,
three spatial dimension, because no. And so for example, this WKB consideration also account for dimensional space, right? Or...
Yes, that's right. So you get a different answer through different dimensions of space here. And what I'm doing here is sort of 3 + 1 dimensions with a string.
Mm-hmm.
Yeah,
I see.
Okay. That's actually very important. Mm-hmm. And it's sort of boring math. It's not particularly useful, but you get bound state energies are of order the charge density, and the bound state radii are 1 over the charge density, sort of just what you expect from dimensional analysis. So normally, if you take this sort of string, charged string, the electric and magnetic fields fall off as 1/r away from it, right? Because now instead of the standard 1/r squared, because it's one less dimension because of the string, 1/r. And so what the bound states do is they act like an atom and they screen electric fields until the bound state no longer fits in that radius anymore. And so since the radius is proportional to 1 over the effective charge density, what you get is that just the final electric field of the screened object as it's moving along is of order 1/r squared. We are not entirely sure how well it screens the magnetic fields. We figure the magnetic fields are probably similarly screened, but they're a lot more difficult to discuss. So the last thing to do is sort of say these wave packets as they move along space, right? If you have a charge density here, in front of it, there's an electric field pointing to the right. Behind it, there's an electric field pointing to the left. And so you get sort of pair production, or not so pair, you get production of particles before and after this sort of wave packet. So this wave packet is spreading as it moves along. And also the fact that the Axion string is a good conductor means that the Axion sort of itself is not losing energy, but everything surrounding it has a lot of interactions. They can lose energy. And so even though an Axion string by itself is a nice superconductor resistance-less object, when you put it in the universe, it interacts with so much other stuff that it is not actually that great of a resistance. It has a non-zero resistance. It sort of dissipates. So, okay, let's actually talk about some signatures. So let's say you have two of these currents and they collide with each other, right? You have left movers coming in from the right and some right movers coming in from the left. These things have 10 to the 8, 10 to the 9 GeV currents, which means when they collide, you can just dimensional analysis your way and see that it's about 10 to the 7 suns in brightness. So these things are like as bright as galaxies when they collide. And so that's sort of exciting, but then you have to ask, well, how often do these occur? And so to see how often they occur, we have to know a little bit more about what strings are like in our universe, sort of how many there are if we let strings occur. And the answer is basically people have numerically simulated strings. There's still some amount of argument, but the rough statement is that there's, roughly speaking, some parameter people like to call C, which is basically a measurement of what's the total length of strings in the universe. And roughly speaking, people have found that there's anywhere between 1 to 1,000 Hubble lengths of strings in our universe. So you can, if they were all in super long strings, you'd have of order 100 to 1,000 strings, Hubble-sized strings per Hubble patch, if they're all in that huge size. But the statement is, yeah, there's just anywhere between 1 and 1,000 Hubble lengths of string in the universe. And this is actually an attractive solution, so it doesn't actually matter how you created these strings to begin with. They'll intersect, radiate tons of axions, and arrive at some number in between here that people doing numerics argue about, and there's no real consensus as far as I can tell yet.
But is it imply certain, I don't know, what is the length of the string? You know, because and yeah. What is the total mass of each string? No, I mean, because it related to their movement, right? I mean,
yeah. So what people have found is that roughly 80% of the strings are in infinitely long strings that wrap around their numerical simulations. So at least 80% of the strings are basically in super long Hubble-sized strings. The other 20% is a logarithmically sort of scale invariant distribution all the way down to very, very small strings. That's roughly the sort of distribution.
Yeah, so it means that it's like a polymer physics, right? Mostly, I mean, in terms of there is a kind of a lot of things, and it could be the same thing, right? Around.
Yeah.
I see.
Do the strings on the inside do anything to electroweak vacuum because you throw in energy scales that are sort of
Yes.
much larger, right? And
Yep.
as we know, E&M is a combination of the two gauge groups, right?
Yeah. So the humongous B field, for example, means that the Higgs gets a ginormous positive Landau level, meaning that it restores electroweak symmetry, for example, around the cores of these strings. And so, yeah, there's a lot of odd behavior around near the center of these strings. Yes. And though that sort of dies off when you get to distances of order 1/100 GeV away from the center of the string. But like near the string, yeah, there's all hell.
There is no immediate observable effect from that, right?
There may be, but nothing we were confident enough to sort of claim. Yeah. But for example, if whatever, they're like, well, I guess the gut scale is too high, but yeah, there may be other observables that we didn't think of. And what we were basically focused on is literally just the total energy of these collisions. And sort of, if you sort of imagine that some reasonable amount of that energy goes into visible light, could we actually see any of this? Or the collisions in particular. So what you can do though, is that given numerical simulation said C is anywhere between 1 and 1,000, we just chose 10. And if you choose a benchmark point of 10 Hubble lengths of string in our universe, you can just calculate the probability of a string crossing a galaxy is about, there are only about 100 of these in the universe right now. So in other words, this is not something that happens all that often. So any observable is going to be of order cosmological distance away. And then because these things are dissipative, then in order for it to have a collision, it has to pass through two galaxies that are pretty close to each other, like within only a few of their sizes in some sense. And this can happen if you have a string passing through a galaxy cluster, because a galaxy cluster has order 100 to 1,000 galaxies in pretty close proximity with each other. And so you can again do some combinatorics math, and you find that of order 10 of these 100 collision or 100 sort of string galaxy crossings are happening inside of a galaxy cluster. And so there are going to be of order 10 collisions at any point given time. So there are only about 10 collisions that are as bright as galaxies, but they're sort of cosmological distances away. And so you can ask then, well, is this at all visible? And don't know if I can explain this plot easily. The statement is, well, forgetting the other lines for now, let's just look at the red line here, which is for some choice of parameters of the 't Hooft anomaly A and the number of strings in the Hubble patch, which again, C in principle should be determined just by numerical simulations. Just people haven't been able to simulate this to high enough accuracy yet. And the statement is the excluded region is this gray thing, which is basically if you can just detect the axions themselves. And you can see that you can probe new regions of parameter space with sort of telescopes looking for these collisions, assuming, of course, we don't know what happens when 10 to the 8, when you have a 10 to the 8 GeV collider, right? These things are smashing with high energy. We just assume that if order 1 in 1,000 of their energy goes into sort of radio waves, which we can see, then sort of CHIME and SKA can sort of exclude a few orders of parameter space that have not been explored yet. And in principle, the sort of benchmarks you like to look at are electric charges unit quantized, which is this line, or sort of 0.3 quantized or 0.3 squared, 1/3 squared, so 1/9. And you can see that, well, if there are not very many strings per Hubble patch, we won't be able to exclude it in the future with SKA. But if they're order 100 or more, then we could actually see these guys.
Yeah, so then I have a question here. So
Yeah.
the natural value for this anomaly coefficient then is basically 0.1 to 1. Would that be a fair?
Yeah, that's right. So that's sort of, I would say, is the benchmark to go looking for.
Because then if you rule that out, then having the anomaly coefficient be 10 to the -3, that's really going to be something unnatural, right?
Yeah.
I don't mean
It'll be
naturalness in the usual
Yeah.
naturalness sense. I just meant
It means the electric charge of the electron is like 10 to the 3 for some reason. And that's just really weird.
Yeah, I see. Yeah.
Yeah. And so that's in some sense what's cool about this is just, yeah.
So another question is
Yeah.
this emission isotropic? Like, is there any preferred direction?
There, order 1, there will be, because what is the probability that both of these collisions have exactly the same energy, right? Because, well, they depend on the B field of the galaxies. And if they're order 1 different, then they're going to have order 1 different energies. And so there'll be a collision and it'll be sort of moving in the direction favoring towards the weaker one, I guess. And it'll be order 1 boosted in that direction. So it'll be more like a cone emitted in that direction.
I see. So you also have to kind of be lucky enough to be.
Yeah.
I mean, that can either help you or
that can help you or hurt you. Yeah.
Yeah. Yeah. Okay. Thanks.
Yep. Okay. So this is sort of the discussion of how sort of you can use the string collisions. I am pretty much out of time. Okay, so I will only extremely briefly here take a few more moments of your time to tell you the opposite effect of just how you can detect these Aharonov-Bohm-like effects using the CMB. I'm not going to derive it, but what you can show is that the polarization rotation or the accumulation of circularly polarized phase of photons when you go around an Axion string is the 't Hooft anomaly times alpha times the change in the Axion. You can use this, you can calculate this using Maxwell's equations, but we don't have time. And so what this means is that if you take a photon around a string, it acquires a circularly polarized photon, acquires a phase of the anomaly times alpha E and M, or a linearly polarized light will get rotated by this amount. And so you can do the same thing for photons passing by a string where 0 to pi, 0 to -pi, and they each get rotated by a bit. Or you can have a string loop where if it passes through the loop, it acquires a phase, and if it misses the loop, it doesn't acquire any phase. Because remember, this depends on just the initial and final values of your Axion field. So it can change by 2 pi or not. So that's the Aharonov-Bohm effect. Let's sort of describe how to look for these. The CMB is the easiest way to look for it because the CMB is polarized, linearly polarized light that is shining on everything between the surface of last scattering and us. And so as it passes by these strings, it can pass through a bunch of string loops and acquire some polarization rotations. And its CMB is nice because we actually even know what direction the polarization should be pointing, because the polarization was produced by Thomson scattering, and in particular quadrupoles. And we actually know what are the hot spots in the CMB and what are the cold spots. So we actually even know the direction for where the CMB polarized light should be pointed to. And so if it's rotated away, we would have seen it. And so there are two ways to look for it. Power spectrum. So this is every CMB person likes the Fourier transform their 2-point function. So that's the power spectrum analysis. Or you can sort of look for these discontinuous jumps in the rotation angle as you sort of, if you're looking and then you cross a string, the polarization rotation jumps. Because instead of going from 0 to pi, it's now going from 0 to -pi on the other side. So what we did is we basically took a toy simulation and we just shone the CMB through it. And depending on the number of strings per Hubble patch of order 100, you get some nice continuous looking thing. 10, you get a little bit less. And at only one string per Hubble patch, you actually just by eye can see the strings. You can literally see the discontinuities across these guys. And so you can just take projections that other people have done and sort of see that if the anomaly coefficient was, in this case, of order 1, if there are of order 100 strings per Hubble patch, Planck actually would have seen this. But if there's only order 1 string per Hubble patch, you would not have seen it yet. These are sort of new experiments on the 5-year and 10-year time scales. And if the anomaly coefficient was 1/9, sort of more like the more pessimistic one to aim for, you'll see that we currently can't really exclude anything. But in the future, 5 to 10-year time scale, we definitely will be able to see something. So since I am basically out of time, I think I'll just sort of jump to the conclusion and sort of say that to me, it's exciting trying to measure these 't Hooft anomalies because they sort of tell you about charge quantization in the ultraviolet of your theory. It turns out strings are a great way to look for them. You can sort of look for these Aharonov-Bohm features in the CMB, which are neat because they're basically searches that are not really being done currently by the CMB community. And the other ones is sort of these collisions from currents on the strings can also give a very bright signal that is also has comparable sensitivity to these sort of Aharonov-Bohm like experiments. All right, thanks a lot.
All right, thanks, Anson. If there are any questions.
Thanks, Anton. That was a sorry. Thank you, Anson. That was a very nice talk. I just to check. So, do Axion strings carry magnetic flux? I guess not.
No,
right?
they do not.
They do not.
Right. They
So
could
that
just
answer is
not even couple to the. They could, for example, not even couple to any of the standard model.
well. They couple. Wait.
So
Axion strings couple to E&M, so they couple to distant.
I guess Axion strings are objects that exist even if they didn't couple to the photons.
Yes, but once they do couple, no,
Well,
wait.
yeah, once they
Yes,
couple to the photon,
once they couple to the photons, they might develop some electromagnetic
yes.
properties. That's your whole talk,
yeah,
right?
they have some topological properties. It's not really B flux that they carry.
But that's good. I mean, they have various electromagnetic properties. That if I understand correctly, that was your entire point.
Yes, that's
and
right.
I am trying to see whether they carry electromagnetic, magnetic flux.
Magnetic
and
flux.
Is the answer no
I
or
believe
yes?
the answer
or
is
you
no.
don't know? You think the answer is no?
Yeah.
So if if it's correct that they don't carry magnetic flux, then it would answer my earlier question in the talk. Because if these Axion strings don't carry magnetic flux, then if you draw a electric Wilson loop that goes around the Axion string by
all right. Yeah, then they would not acquire.
They would not acquire. That expectation value of that Wilson loop would be trivial because you can relate it to the magnetic flux carried by the string.
Yeah, that's correct.
Okay.
Wasn't there a
check this?
Sorry, wasn't there a current on the string?
So you could
Current,
create
which would give
currents
rise
on the
to
string.
in the presence of a background electric field. That's right.
Yes, that's right.
But without a background electric. Okay. I see.
So you could induce a current onto the string, but if you took a string by itself with no charge or no current on it, then there's no
Right.
beef.
There's no beef.
But just perturbatively, if you have axion interacting with, say, 2 photons, then you can couple those photons to your fermion. Okay, would it generate interaction of axion with your fermion? Yeah.
So at one loop, you do get sort of the coupling to photons turns into a coupling to electrons and works and everything. Yes.
I see.
That's right.
And this one would be, kind of, no, it would be small coupling, right? But I mean, it doesn't have any kind of anomalous behavior, right? So this one, I mean.
It's also harder to, experimentally, it's harder because we see photons from very, very far away. We don't really see very many electrons from very, very far away. And so I think that's sort of mostly the reason why I focused on photons.
But I mean, you produce all sorts of stuff, right? So maybe you also get some neutrino flux from this. And...
Yeah, so like in the collisions, you probably get a large number of neutrinos. You probably get a large amount of pretty much everything. Probably even particles we don't know what they are yet, because this is our 10 to the 8 GeV collisions.
Yeah. So Anson, can I try to understand what's the basic state of those strings? Now, are the current induced on the string in a certain environment, or
yeah? So they're induced by electromagnetic fields.
So if the string came across any external magnetic field, then there will be induced current on them. Right. And the string presumably can cross over different regions which have a different direction from the magnetic field.
That's right.
How would the current flow? They annihilate,
so
or
you have a current going up and then another current coming down that sort of collide and then disappear.
Okay, so that's a collision you're talking about, or in the beginning I thought you were talking about string collisions, but you're actually talking about the current.
These currents on the string.
Oh. Okay.
Sorry.
I see. And you're also talking about the screening effect, right? I have a strong current in the local region. I would have other oppositely charged particles or charged particles.
So it's not just a current; it's a current plus a huge number of bound states, right? Because these bound states have bound state energies of 10 to the 8, 10 to the 9 GeV. Like they're just very, very tightly bound to your string.
And where does this energy scale come from? The decay constant, or
no? It comes entirely just from b times the distance times the velocity, sort of just whatever Faraday's law type thing of d flux dt type currents.
So if these strings collide and reconnect, can this happen? And then typically people also discuss, relaxation of the edge, right? When you reconnect, you have a sharp edge and then it relaxes. Here you drag a lot of charge. Maybe there is like additional E&M radiation from after the collision. That's what I'm saying.
Yeah. So for example, if you just had one of these kinks, then a photon going through the kink might just sort of go, or sorry, the current going through the kink might just get thrown completely off and things like that if it has enough energy. And so you could get other odd behavior when you combine just the fact that strings aren't straight lines with these things.
But do they reconnect like the strings?
I think the statement is we're not entirely sure. The electromagnetic forces may help or hurt this. I guess if they're opposite charge, you can sort of take strings and sort of pull them in to sort of crossing. And if they're opposite, then it'd sort of push them away. We haven't really thought in detail about it, so we're not entirely sure.
Okay.
I think these currents tend to be, they're sort of required to have energy less than the strings themselves. So it's not entirely obvious that actually the currents would change much about the sort of string behavior. They may just be like, oh, they're dominated by their tension, so all these effects are smaller than the tension. So maybe that makes it more calculable, because then if it doesn't change reconnection, then maybe you can just treat it as in perturbation theory or something.
Hey, Anson. So I have a question about your assumption about the axion being massless. So if I understand correctly, the reason you have to assume that is that you need to avoid the domain wall problem.
Yeah.
So I'm wondering what would happen if, in two cases, if I assume domain wall number equal to 1, or if I assume some explicit breaking into the U1 symmetry so that the domain walls are unstable, would any of your work still apply in that case?
So if domain wall number is 1, then what happens as soon as Hubble is of order of mass is you create domain walls and they just sort of pull all these strings to nothing and the strings just disappear. So for example, this is what happens for QCD Axion strings. In the early universe, Hubble becomes of order of their mass, and then they all disappear.
Yeah.
And so for n equals 1, you just need the Hubble of when we observe them is larger than their mass. So they didn't disappear by CMB, or they didn't disappear by today.
Yeah.
If you had domain wall number not equal to 1, then you'd get a lot of the same effects. You just have to be very, very careful about not overclosing the universe.
Mm-hmm.
And also, I guess, there's like Zeldovich type bounds on domain walls, which are slightly stronger than overclosing, things like that.
Mm-hmm.
And so the statement is it's still possible, but it's a little bit harder to implement in practice.
Uh-huh. And what if you introduce explicit symmetry breaking?
Explicit symmetry breaking, what would happen? I think that would just, what that does is it decouples when they're destroyed from Hubble equals m. And so you just have to make sure that that explicit breaking doesn't destroy the string network before CMB, let's say, if you want to see some CMB effects.
Uh-huh. I see.
Yeah.
Thanks.
Any more questions? Okay, if not, thanks so much, Anson. That was very interesting. I'm gonna stop the